Section 5.3, example 13, using divergence test. Before we start, a divergence test, all we're doing is looking at the limit as n approaches infinity of a sub n. If we take the limit of this infinite sum and it equals a value or does not exist, then the series diverges. So I know it sounds weird, it's kind of opposite of what we've been doing, but the series here is going to diverge. So looking at this first one and applying the test. So the limit as n approaches infinity, 3 to the n minus 1 over n. We apply this. And actually it's not to the n minus 1, it's 3 times n. So 3n minus 1. Much easier. Much better. Okay, so 3 to the 3n minus 1. And we could divide both top and bottom by n. So we have 1 over 3 minus 1 over n, which this part goes to 0. So our solution ends up just being 1 over 3. And because 1 over 3 is not equal to 0, then we would say that this series diverges. So that's part A. Let's take a look at part B. So now taking the limit as n approaches infinity of 1 over n cubed. This ends up going to 0. As n gets larger and larger, it goes to 0. And here we cannot say that it converges, nor can we say that it diverges. What we have to say is that it's inconclusive. So by the divergence test, this is inconclusive. By the divergence test, this diverges. And lastly, looking at this one, we have the limit as n approaches infinity of e to the 1 over n squared. So 1 over n squared. This goes to e to the 0, which ends up being 1. And we know that 1 is not equal to 0. So this diverges. Based on the divergence test, this function, I can't even write today. This function diverges. And there we go. So we know that some functions or some series converge continuously or absolutely. Some diverge, some converge conditionally. This is going to help us determine where these values are. Is it conditional? Is it continuously? Is it absolutely? Or does it just diverge? If you have any questions, please feel free to ask. Otherwise, bye.